Thank you very much for the introduction and also for giving me the possibility to talk at this seminar. So this talk will be about the rectifiability of CDKN spaces with unique tangents, and I will assume you're not all familiar with CD spaces. So I will spend the first part of the talk introducing these objects and highlighting in particular the properties that are relevant for us in the context of this presentation. So before starting, I would like to remark that CD stands for curvature dimension bound, and the CDKN condition is a synthetic curvature dimension bound, which is defined in metric measure spaces. And it is synthetic, of course, because in metric measure spaces the notions of curvature and dimension are not necessarily well defined. And in particular, K will represent the lower bound on the Ricci curvature, the synthetic lower bound on the Ricci curvature, and N will represent the synthetic upper bound on the dimension of the space. Okay, so before giving you the definition, I would like to start with a motivational slide in which I would like to convince you that Ricci lower bound controls volume growth along geodesic flows. So in particular, this is a smooth slide. So we have a Riemannian manifold Mg with dimension n, and we equip it with the usual volume measure, the associated volume measure, and we assume to have a lower Ricci bound of this type. So we assume the Ricci curvature tensor to be bigger than or equal to k times the metric tensor G. And now we want to study volume distortion along the geodesic flow. And to this aim, we fix x bar in M. We consider a vector field psi defined in the neighborhood of x bar. And we consider an orthonormal basis of the tangent to M at x bar. And for every delta small, we define p delta. We call p delta the infinitesimal cube of size delta in the direction of the orthonormal base. Now we basically define the geodesic flow in this way. So for every t in 0, 1, we will define the map tt, and tt of x will be essentially the geodesic starting from x in the direction k of x, evaluated at time t. So in this way we have really a description of the geodesic flow associated with psi. And this is a picture of what's happening. And of course we will consider p delta and then tt of p delta, and we want to understand how the volume changes. And to do so, we will consider the quantity jt, which is the infinitesimal volume distortion, and therefore it is the ratio between these two volumes as delta goes to 0. And for simplicity, we consider this quantity d, which is j to the power 1 over n, where n is the dimension of the manifold. And doing the explicit computation, we can actually prove that this differential inequality holds. And in particular, the volume distortion is controlled by the Ricci curvature tensor along the base curve gamma. And in particular, if we have a lower curvature bound k, we have also this inequality, and therefore the volume distortion would be always controlled for every geodesic flow by a quantity that's depending only on the Ricci curvature bound, lower Ricci curvature bound. So the takeaway of this slide is that the lower bound in the Ricci curvature allows to control volume growth. And this was the basic observation behind the CD condition. So now we can really go to the definition of the CD condition, but before starting we have to introduce a couple of fundamental objects to define it. And as I was mentioning before, the CD condition is defined for metric measure spaces, so spaces of the type XTM, where XT is a complete and separable metric space, and M is a locally finite Borel measure on X. And the two fundamental objects are both defined on P2 of X, which is the space of probability measures with finite second order moment. And the first fundamental object is the Wasserstein distance W2, which is a distance between measures in P2. So given mu and nu in P2, the Wasserstein distance squared between mu and nu is defined as the infimum of this optimal transport problem. In particular, and this is a minimization over all admissible plans, which are measures in the product space X times X, having mu as first marginal and nu as second marginal. And if you want, these admissible plans represent all the possible ways to move the mass from mu to nu, and among all these possible ways we want to find the minimal one according to the energy function, which in this case is the integral of the distance squared. And the result of this minimization will be the Wasserstein distance squared between mu and nu. Okay, so this was the first fundamental object. The other one will be the Ricci entropy functional. And the Ricci entropy functional is defined according to a dimensional constant, capital N, and is a functional defined on P2. And for a measure nu in P2, Sn of nu is equal to the integral, minus the integral, sorry, of rho to the power 1 minus 1 over n with respect to the reference measure, where rho is the density of the absolutely continuous part of nu with respect to the reference measure n. So a final remark before going to the definition is that now, as we assumed xd to be completely inseparable, then also P2 with the Wasserstein distance will be completely inseparable. And moreover, the Ricci entropy functional is lower semi-continuous with respect to the convergence induced by the Wasserstein distance. So these two objects are quite nice, and they also interact quite nicely with each other. Okay, so then we are ready to give the definition of the curvature dimension condition that was introduced by Sturm and Lott-Villani. And as I was saying before, this is usually given in terms of two constants, k and n. K represents the lower bound on the Ricci curvature, and n the upper bound on the dimension. And in this first slide, I will introduce this condition for k equals 0 because it's the easiest case. And in the case k equals 0, we say essentially that, so this is the formal definition, but basically the CD0n condition is the convexity of the n Ricci entropy functional in the Wasserstein space. And this means that for every pair of measures mu0, mu1 in P2, there exists a Wasserstein geodesic, mu-t, connecting them, and with geodesic I simply mean a length minimizing curve in the Wasserstein space, such that the Ricci entropy, the n Ricci entropy is convex along it. And this condition may seem a little weird, but in some sense it is the right one according to this theorem, which in its first form appeared in this paper by von Rennes and Sturm. And this is a smooth theorem, and basically says that given a Riemannian manifold of dimension n, then the associated metric measure space m with the Riemannian distance and the Riemannian measure is a CD0n space if and only if the Ricci curvature tensor is greater than or equal to 0. So in particular, this theorem is saying that in the smooth setting where both the notion of curvature and the notion of dimension are well defined, then the CDKN condition is equivalent to a Ricci bound. Therefore, the CD condition is a consistent curvature dimension bound in the non-smooth setting of metric measure spaces. And in particular, the advantage of the CD condition is that it is synthetic, meaning that it's only defined using a metric and a measure, and therefore it can be taken as a consistent curvature dimension bound in the non-smooth setting of metric measure spaces. Indeed, this fundamental theorem by von Rennes and Sturm also holds in greater generality, for example, for a weighted Riemannian manifold, so manifolds in which we also add a weight in front of the volume measure of this type. Now, the right Ricci curvature tensor we have to consider is this generalized one. But considering the right Ricci curvature tensor, we still have our equivalence result. So weighted Riemannian manifold is CD0n if and only if this generalized Ricci curvature tensor is greater than or equal to 0. And moreover, everything holds quite nicely even if we now consider non-zero k. It's possible to adapt the CD condition also for a non-zero case in the following way. I will not go through the definition, but just remark that there is suitable generalization of the CDKN condition also for k not equal to 0. It's a bit more complicated, but once again, it is the right one according to this equivalence theorem. Indeed, for a weighted Riemannian manifold, so a weighted Riemannian manifold is a CDKN space if and only if the generalized Ricci tensor is greater than or equal to k times the metric tensor. So in particular, even in this case, we have equivalence, and therefore, in general, the CDKN condition is a consistent curvature dimension bound for metric measure spaces. Okay, so the reason why this CDKN condition was so successful is that CDKN spaces actually enjoy a lot of nice properties, and the first four I've listed here are actually reasonable for a curvature dimension bound. For example, the monotonicity in terms of these parameters, and the scaling property that basically is reminiscent to what happens in the smooth setting. So if we change the measure, the constants don't change, and if we scale the distance, the curvature changes and the dimension doesn't change. So these are reasonable properties. And then there are a couple of non-trivial ones. The first one is the globalization property, which was proved in its final form by Cavalletti and Millman, which basically states that if the CDKN condition holds locally in the whole space, then it holds also globally. And so this is of course very reasonable, because if we think as the CD condition as a curvature dimension bound, then the Ricci curvature tensor is a local object. So of course, if the bound holds locally, then it also holds globally. But the CD condition is not defined in a local way. So this is non-trivial, but it's true. Okay. And then probably what is the most important property of CD spaces is this ability with respect to the measure of Gromov-Hausdorff convergence. And even if you're not really familiar with this convergence, you can think this as a very natural convergence for metric measure spaces that combines the Hausdorff convergence for the metric side and the weak convergence for the measure side. And the point is that the CDKN spaces are closed with respect to this convergence. So if we have a sequence of CDKN spaces converging with respect to this topology to another metric measure space, then also the limit is CDKN. And this is quite relevant because the same result doesn't hold for smooth Riemannian manifold. And the point is that a measured Gromov-Hausdorff limit of smooth Riemannian manifold is not necessarily smooth. So the class of smooth Riemannian manifolds with a lower Ricci bound is not closed with respect to this convergence, while CD spaces are. So if you want, CDKN spaces are a class of spaces that is closed with respect to this convergence and contains all the Riemannian manifold with that curvature bound. And then we also have other geometric properties like these ones, which are usually like geometric or functional inequality on the space that hold in the smooth setting and hold also in the non-smooth setting, and were actually already proved in the first paper by Sturm. And so in this picture, it seems obvious that CD spaces are quite nice, so they have a lot of properties, of geometric properties, but of course they're lacking something, and they're lacking in a smooth structure, which is actually very relevant in the study of Riemannian manifolds. So in general, the problem with these spaces is that developing an analytic study of these spaces is very, very difficult because they are non-smooth. So in general, it's very difficult to prove finer geometric results because no analytic tool basically is available. And this is why their geometric structure these days is not really understood. And to overcome this problem, it was actually it was a need to introduce this infinitesimal Hilbertian assumption that now I'm going to describe. And this infinitesimal Hilbertian assumption is given in terms of this Shiger energy functional, which is defined in a metric measure space for every function in L2. And this is defined with relaxation procedure. Once again, I'm not really interested in the definition. The point is that this Shiger energy functional is the metric analogous of the Dirichlet energy functional. So 1/2 integral of the norm of the gradient squared. And yeah, so in nice metric measure spaces, it's possible to define this figure energy functional, which is a replacement of the Dirichlet energy. And with this, we can define the infinitesimal libertianity, which basically only asks the Chigger energy to be a quadratic form on L2, so the Chigger energy to satisfy this parallelogram identity for every pair of functions in L2. And pairing, so this was the basic idea, and then RCD spaces were introduced by Ambrosi, Gillian, Savare, and Gini for the finite dimensional case. And in general, RCD KN spaces are just CD KN spaces satisfying this infinitesimal libertianity assumption. And the idea is that this infinitesimal libertianity assumption forces the space to be locally similar to a Riemannian space. And indeed, this R in RCD really stands for Riemannian. And in some sense, this adds structure and forces your space to be Riemannian-like. For example, Ricci limit spaces, meaning measured Gromov-Hausdorff limits of Riemannian manifolds, are RCD spaces, and of course also Riemannian manifolds are RCD spaces, while for norm spaces this is very different, because if we have Rn with a norm and Lebesgue measure, now this is RCD even only if the norm is induced by a scalar product. So the RCD condition is really identifying the spaces having a distance which is more or less induced by a scalar product. So it's quite restrictive if you see it in this way, but it's also very natural because yeah, this is what happens in Riemannian manifolds. And indeed, this was also very reasonable because it allows to define a lot of analytic objects, for example, the Laplacian, the heat flow, and then you can generalize these analytic objects and you can develop an analytic study of RCD spaces, and in this case you are able to prove finer geometric results building on this analytic structure given by the infinitesimal libertianity. So in general, RCD spaces are nicer, and it's actually possible to prove remarkable result in these non-simple spaces. And one of those is actually rectifiability. And in this talk I will use this definition of rectifiability. So I would say that a metric measure space XDM is n-rectifiable if there exists a countable collection of Lipschitz maps defined on Borel subsets of Rn, such that X is M almost all covered by these images. And this is not necessarily the same as the classical definition of n-rectifiability, because usually in n-rectifiability you would like to have the Hn measure here. But for a reason that will be clear in a second, we prefer to have M here. And the idea is that we already have a reference measure here, and we already have a class of null sets, so we might as well take these as null sets. But I will make a remark at the end of this slide, and this will be definitely clear. So, the point is that RCD spaces are rectifiable, and this is a theorem by Mondino and Neber. So, every RCD space is rectifiable, meaning there exists an n such that it is n-rectifiable. And Mondino and Neber's result was then improved in some sense by Drouet and Semola, who proved that there exists an effective dimension NE, such that at almost every point the metric tangent is Euclidean with dimension NE. So even if you don't know exactly what a metric tangent is, the point is that the metrics, so an RCD space looks like an Euclidean space of dimension NE at almost every point. So the dimension is really constant throughout the space. Okay? So indeed, this result is called constancy of dimension. Okay, now the remark I promised is the following, is that the effective dimension is not necessarily equal to the Hausdorff dimension of the space. And this is according to an example constructed in Pan and Pan Wei. So in this case, the Hausdorff dimension of the space is bigger than the effective dimension, which in some sense is the rectifiable dimension. So the effective dimension, according to this, is the rectifiable dimension, and in general the Hausdorff dimension of the space is bigger. So this is the reason why we don't put the Hausdorff measure here, because putting the Hausdorff measure, this result will not be true. So this is the right definition of rectifiability in metric measure spaces. So
with this definition, so if the space is n-rectifiable, then it's also n plus 1 rectifiable.
Yes.
That's something you would like.
Yes. If you want, so the point is that if you put Hn here, now according to this example, this result is not really true. So you might have m null sets, which have a very big Hausdorff dimension, and so you would like to consider null sets with respect to the reference measure instead of the Hausdorff measure.
No, so this I understand, but just so that your maps, so that your subsets, so that your maps Fi, so usually if you have an n-rectifiable set,
Okay.
Then these maps Fi, you can use them to be bi-Lipschitz.
Yes. So indeed, actually, this theorem is not exactly this sentence here. It's more detailed. There is a stratification, and in every stratum you have a bi-Lipschitz map. So this result is more detailed than that, but for the purpose of this presentation, this is enough if you want. But yes, with this definition, what you say is true.
Maybe in the vision way is enough to take AI in Rn, where this small n is minimal. It is the minimal.
So, yes. Okay, is it clear? Okay. Okay, so in RCD spaces, everything is very nice, and in the next slide, I would like to convince you that in CD spaces the situation is much more complicated, and I would like to show to do that with an example, and this is the example. Yes.
Sorry, the previous result, if you have RCD Kn and the essential dimension is Ne, then the space is also RCD Kne, or sorry?
Yes. No.
Take a weighted manifold. Then take, for instance, R2 with the weight, and with the weight you make with the Barbieri 3, So the Ne is 2 or 2, but the n of the RCD Kn it comes from the weight.
So I got the question wrong. So was this the answer?
Yeah.
Okay. Well, I understood that the question was that if this was the rectifiable dimension. So in general, this is the rectifiable dimension. This is true. So Ne is the rectifiable dimension, but in general, the n of RCD Kn is bigger.
But what I was asking, like, if you can improve the dimension parameter so that you now have RCD
No, this is not true. Yes. Okay, so back to the example. The example is the following. So the example is a subspace of R2, which is defined as the union of an half line and a cone, Ck. So K represents the width of the cone. And on this space, we define this measure, and even if without really going into the formulation of this measure, the important part is that this measure is a constant times the H1 measure on the line and a positive density times the Lebesgue measure on the cone. Okay? And then we metrize this with the distance induced by the L infinity norm. And for suitable choices of the constant, then this metric measure space satisfies the CD0n condition. So this shows in particular that the constancy of dimension cannot hold for CD spaces, because in this case, of course, you have two positive measure parts of our metric measure space, and this has dimension 1, of course, and this has dimension 2. So in general, the constancy of dimension that was proved by Burel-Semra cannot hold in CD spaces, and this already shows that the situation in CD spaces is much more complicated. And for this reason, we had to come up with a different strategy for proving rectifiability in CD0 and in CDKN spaces, and this strategy relies on the notion of sub-Finsler kernel groups. So I will introduce these objects in this first slide. I will start using the language of Lie groups, and if you're not familiar with this, it's not very important. The important part comes after, which is the geometric structure of these spaces. Yes?
Sorry, in the example you showed, that was a branching space, right?
Yes.
Are there examples like of non-branching
No.
CD spaces?
With non-constant dimension, no, at the moment. No.
Okay. Thanks.
Okay, so a kernel group in general is a connected and simply connected Lie group with an important Lie algebra that admits the certification of this type. So in general, in a Lie group, you will have an identity element, it will be called E, and then the tangent to the group at the identity element will admit a certification of this type, where we also have that Gi plus 1 is the bracket between G1 and Gi. Okay, so these are subspaces, so yeah, this is the bracket between every vector in these two strata. Whatever, so this is the proper definition, but the important thing is that once you have this structure, at every point you can define a left invariant subbundle D, which is called the distribution, and you can define using the left multiplication of the group. So the result of this construction is that at every point in the tangent space we will identify a subspace of the tangent that will be our set of nice directions. So the idea is that at every point we will have a subspace of the tangent. And on this subspace we will induce a norm, so we will fix a norm on G1, and then by left translation we will induce a norm on the distribution at every point. So the result of this complicated construction is that at every point we have a subspace of the tangent and we have a norm which is defined only on this subspace. So this is different from the Riemannian case in which a norm is defined on the whole tangent space. But then essentially we can try to define a distance in an analogous way. So usually in Riemannian manifolds you take 2 points and then you connect these 2 points with all the geodesic, all the lengths, and then so you take 2 points and you consider all curves joining these 2 points. You compute the lengths of these curves, and then you minimize among all the lengths. Okay, and then you end up with the Riemannian distance. And then you would like to do something similar, but of course you cannot do exactly the same, because now you have only a norm defined on the distribution, so you cannot really compute the length of curves which have velocity not inside the distribution. So in this length minimization procedure, you just consider admissible curves gamma, and admissible simply means that gamma dot is inside the distribution at every point, and being a vector inside the distribution, you can really compute the speed at every point because the norm is defined on the distribution, so you can compute the speed. Then you can integrate the speed and get the length of the curve. Okay? And then you minimize and you obtain the so-called sub-Finsler distance. There is a theorem, the Chorashevsky theorem, that guarantees that this is a finite distance, so it's a nice distance. And this is the sub-Finsler distance, which is on our kernel group, and it actually, of course, depends on the norm we fixed on the first layer of the stratification. So these are sub-Finsler kernel groups, and this is the main example, the main non-trivial example of sub-Finsler kernel group, which is the Eisenberg group. So the Eisenberg group is basically R3 with this non-commutative group law, and coming back to the formulation with respect to Lie groups, this is the stratification, so G is G1 plus G2. G1 is the horizontal plane and G2 is the z-axis. Once again, not really interested in this. The point is that now we can define the distribution as we did before, and the distribution now is generated by these 2 vector fields at every point. So the distribution will be a subbundle of dimension 2 in R3. So this is a representation of the distribution on the horizontal plane in R3. So now, what happens, for example, if we want to start from the origin and find a geodesic connecting the origin with a point on the same vertical is that we cannot go straight up because the distribution in the origin is horizontal, is this first layer here. So the point is that we cannot go straight up, so to find a geodesic we will basically have to move a little bit and start horizontally to fill these contributions in the vertical direction and then starting to go up gradually until we can come back to the z-axis. And indeed this is exactly what happens, for example, in the sub-Riemannian Heisenberg group, which is the Heisenberg group in which we put the Euclidean norm in the first layer. The geodesics are circular spirals like the one represented here. So as I was saying, the Heisenberg group is the easiest non-trivial example of Carnot group, and I'm specifying non-trivial because in this case the stratification is non-trivial, but of course it can be trivial. You can have only one stratum, and in that case you end up with a Banach space. So in particular, Banach spaces, so finite dimensional Banach spaces are Carnot groups, but they are in some sense trivial because you don't have a non-trivial stratification. But keep in mind that Banach spaces are indeed Carnot groups. Okay, so now a very natural question, why sub-Finsler Carnot groups? Why am I talking about sub-Finsler Carnot groups? The first answer is that sub-Finsler Carnot groups are the only metric spaces that are locally compact and geodesics, isometrically homogeneous, meaning that the group of isometry acts transitively, and self-similar, that means that they admit dilation. Now, even if you don't exactly know what these are, the point is that sub-Finsler Carnot groups are the only spaces satisfying this set of metric assumptions. So you can really identify sub-Finsler Carnot groups as the only metric spaces satisfying a set of metric assumptions. And this is quite remarkable because indeed sub-Finsler Carnot groups have a structure. So it's quite remarkable that just asking these three conditions, you end up with something having a structure. And as a consequence of this, if you want, sub-Finsler Carnot groups naturally arise as metric tangents of metric measure spaces. So first of all, what is a metric tangent? If you don't know. So the point is that we take a metric space and we say that a pointed metric space, meaning a metric space with a distinguished point, is a metric tangent if there is a sequence of rescalings of this type that going to zero that converge in the Gromov-Hausdorff point Gromov-Hausdorff convergence to this space. Now, once again, the pointed Gromov-Hausdorff convergence is a very natural convergence for metric spaces, which is the metrical adaptation of the Hausdorff convergence. And what happens here is that you take your metric space and then you fix a point, and then around that point you zoom in further and further, and you say that you converge to something at some point with respect to this convergence, and you call this something a metric tangent of the metric space at that point. In particular, if you are in a smooth manifold, then in a smooth Riemannian manifold, then the metric tangent at point is exactly the tangent space at that point with the scalar product at that point. Of course, in general, for metric measure spaces, the situation is a little bit more complicated because the metric tangent is not unique at every point. It might happen that the tangent is it's not necessarily a unique space, and in particular, we will call tan capital X X the set of all metric tangents of capital X at X. Okay. And then to the theorem, which was proved by Ledonne after the work of Berestovsky and Price, is that if we have a geodesic metric space XD equipped with a nice doubling measure, and if we assume that at almost every X the set of metric tangents contains only one element up to isometry, then at almost every X, this element it's sub-Finsler Carnot group. So if the tangent is unique almost everywhere, then it is almost everywhere a unique sub-Finsler Carnot group. And in this sense, sub-Finsler Carnot group naturally arise as metric tangents of metric spaces. And this is quite remarkable. So only asking uniqueness of the tangent, we get that the tangent also have have a lot of structure, so they are subfield kernel groups. And building on this, we developed a different strategy, different from the RCD setting, to prove rectifiability for CD spaces. And this strategy essentially builds on this conjecture. And after a series of work in sub-Riemannian and subfield geometry, this conjecture is actually very reasonable. At this point in time, this is still a conjecture, but it's very reasonable. And the conjecture basically says that if we have a subfield kernel group equipped with a nice measure, then if this satisfies the CDKM condition, then we actually have a trivial subfield kernel group, meaning a Banach space. So the conjecture is basically saying that if a subfield kernel group with a nice measure satisfies CD, then it must be a Banach space. And at this point, as I was saying, this is still a conjecture, but there is reason to believe that this conjecture should be true. Okay, and building on this conjecture, we can develop this strategy to prove rectifiability of CD spaces. So let's start from a CDKN space and suppose that at almost every point there exists a unique metric tangent. Okay, so the tangent is unique, so we are exactly in the assumption of this theorem. Okay. Then there will be a nice measure Nx on this tangent, such that now this sequence of rescalings that also takes into account rescalings of the measure converge now with the pointed measure Gromov-Hausdorff convergence to our tangent space equipped with this nice measure. This is a non-trivial result, but if you want, it's a consequence of Gromov-precompactness theorem. But okay, I'm being sketchy in this slide. This is just to give a rough idea of the strategy. So once again, this is the pointed Gromov-Hausdorff convergence, in which you also had weak convergence of the measure, basically. And now if you have this, almost everywhere we have two consequences. The first is that this metric measure space will be a CD0n space. And the reason is that the CD condition is stable with respect to the measure Gromov-Hausdorff convergence, so the limit will be a CD space. Okay? And the other thing is really a consequence of Lott-Sturm-Villani's theorem that I showed before, is that the tangent space is also a subfield kernel group. Okay? So now subfield kernel group that's also a CD space, then we can use the conjecture, and the conjecture says that if this happens, then the tangent space should be a Banach space, almost everywhere. And this would be sufficient to conclude rectifiability according to a result by David Bate, which is exactly the result then presented in the winter school in this program. This is not exactly the statement, but once again, it's possible to fix the details. So this is the idea. It's assuming that the metric tangents are unique almost everywhere. Then we will see kernel groups at the limit. Then we'll use this conjecture to prove that the tangents are Banach almost everywhere, and then using Bates' result to conclude the rectifiability. Okay. All right, and using this strategy, we were able to prove two results. The first one is a result for small dimensions that builds upon this theorem here that basically states that the conjecture is true in the Heisenberg group. This result says that if we have a subfield Heisenberg group with a nice measure, then the CDKN condition cannot hold in the Heisenberg group, and this is coherent with the conjecture because now of course, the Heisenberg group is not a Banach space, and we see that the CD condition cannot hold in the Heisenberg group. And building on this, we have this theorem, and before stating it, I'll introduce one last notion, which is the notion of locally M-Alfors regular measure. Now, without going into the details, a locally M-Alfors regular measure is a measure that, for small scales, behaves like R to the power M, up to constants. Okay, so this is the definition of locally M-Alfors regular measure, and this is the theorem. So if we have a metric measure space X Dm, which is CD, and we have these two assumptions. So the first one is that the reference measure is locally M-Alfors regular for some m between 1 and 5 excluded, and the set of metric tangents is a unique element at almost every point. Then we can prove that M is integer and that our CDKN space is M rectifiable. And I said that this result builds upon this theorem because essentially the point is that subphysical kernel groups are classified for small. So this is a result for small Hausdorff dimensions, so Hausdorff dimensions strictly less than 5. And the point is that kernel groups are classified for small dimensions, and the Heisenberg group is the only non-trivial kernel group with Hausdorff dimension strictly less than 5. So using this result, we are able to prove this theorem. Okay? But this, of course, is only for small dimensions, and then we also have a result for any dimension, but we have to add a couple of assumptions. And the first one is this one, and I will not go into the details of this, but this assumption is called infinitesimal strong convexity, and it's an analytic assumption, if you want, which is reminiscent of infinitesimal libertianity, but it's actually much weaker. So this is analytic, meaning that it's formulated in terms of the Cheeger energy as infinitesimal libertianity. But it's also much weaker according to this remark here, and in this case Rn with a norm and the Lebesgue measure is infinitesimally strongly convex, if and only if the norm is strongly convex. Okay? And of course all norms induced by a scalar product are strongly convex, so this assumption is definitely much weaker than infinitesimal libertianity. Okay? And yeah, so with this assumption we're able to prove a theorem for every dimension, which is the following. So if we have a CDKN space, we have now 3 assumptions. The first one is that the measure is locally n force regular. Quick remark now, n is the same of this n. So now the n, so the Hausdorff dimension basically is now the same dimension of the dimensional bound. Plus, we assume our space to be infinitesimally strongly convex, and as before, we assume the tangent to be unique almost everywhere. And with this assumption, once again, we're able to prove that n is integer, and our CDKN space is n rectifiable. So, quick recap. So, for small dimensions, we have this result that basically only have one strong assumption, which is this one, that the tangent is unique at almost every point, while for every dimension we have a more general result with a couple assumptions more. This is an analytic assumption, and this is, if you want, is a non-collapsing assumption. Okay? Non-collapsing meaning that the n of the CDKN condition is equal to the Hausdorff dimension. And yeah, that's it. So thank you for your attention.